Hey, my name is Werner. I'm a mechanical engineering student, and I worked alongside with Liam Weeks and Valentin to arrive at our final product here. So this is our capillary viscometer. So it's broken down into three major components. So we have a machined upper barrel, a machined lower barrel made out of aluminum, and then we have these steel capillaries. We have four. So they're broken up into 2-inch and 3-inch lengths and 2 millimeter and 3 millimeter inner diameters. So that allows us to capture viscosities over a wider range, which is required when you're doing things like wax injection molding, because depending on the geometry and the surface finish and your mechanical strength requirements of casting, you'll want to inject at various viscosities. So breaking down our design here, our capillaries fit into the lower barrel where they're housed, and the upper barrel is affixed to it. So we use an O-ring and a gland to flush up these two surfaces, and then we screw up from underneath through blind holes, 1/4x20 socket head bolts. At that point, we'll affix our sensors. So the working principle of this unit is we're measuring the static pressure of the wax in the upper barrel, and we're measuring the wax's temperature. So we achieve this by using a Honeywell pressure sensor, and this is capable of up to 3,000 psi. We affix this to the upper barrel, and we also affix this Type J thermocouple. So it has a 3/8 insertion depth, and it's mounted with a brass-collared fitting. Additionally, we need to keep the entire unit at a constant temperature. So we'd like to keep this at a temperature very close to the temperature of the wax that's flowing through it. Because if we're changing the temperature of the wax, we're changing the viscosity, and we can also run the potential of having wax freeze inside the unit. So we use a Type K thermocouple, and that's screwed into the lower housing, and that communicates with our temperature controller. So what this does is it tells these 6 cartridge heaters how much wattage to output in order to maintain a temperature. So once that control point is reached, we'll maintain the temperature, and we'll keep cycling with positive feedback and keep the temperature constant. So how do we flow wax through this unit? Well, from the Model 55 wax injector, we're providing the unit with a constant flow rate and temperature of wax. And that allows us to use the Hagen-Poiseuille flow equation. And what that tells us is when we know the pressure difference at the entrance and the exit of a capillary, we can measure its viscosity. When it comes to non-Newtonian fluids, we need to do something called power law indexing. And that correlates the shear rate in which the shear strain rate, rather, that we are flowing the wax through the capillary at to the new viscosity that's created. So in less formal terms, the rate at which you shear or deform the wax changes its viscosity in the capillary. And we also use something called the Rabinowitz correction and the Bagley entryway pressure drop to make our measurements more accurate. So I'm going to pass this off to Myles Barcelo now. He's our computer engineer, and he'll tell you all about our electronical control box.
Hi, I'm Myles Barcelo, the computer engineer of the group, and let's take a closer look. The electronic control unit of the capillary rheometer involved the connection between the Honeywell ABHP 2000 pressure transducer and the Type J and Type K thermocouples. This is achieved by the utilization of a Raspberry Pi 4's general purpose input-output ports, or GPIO, and more specifically, the Serial Peripheral Interface Bus, or SPI for short. The SPI bus is a serial communication interface which allows a user to synchronize multiple short-distance communication peripherals with a single board. All the peripherals in the SPI bus share 3 signals: master output slave input, or MOSI signal, the master input or slave output signal, or MISO, and the serial clock signal. These all drive the data acquisition into each of the peripherals per clock cycle until it is referenced by a controller into utilization. This is achieved using the chip select signals, which is the main enabler for the Raspberry Pi to acquire these readouts. In the context of the rheometer, the Raspberry Pi has dedicated pins for the MOSI, MISO, and serial clock signals. I utilize the Adafruit CircuitPython digital I/O library to use any of the GPIO pins as a chip select rather than the Raspberry Pi's 2 dedicated chip select pins. This allows us to connect all 3 peripherals together with no problem. The thermocouples are connected to 2 Adafruit Max breakout boards, which acquire the analog signals from the thermocouples and converts it into digital signals natively along the integrated chip. As for the pressure transducer, a voltage reader was connected at the end of a signal conditioner to acquire a raw analog voltage signal between 0 and 5 volts. The voltage is then passed through the MCP 3008 analog to digital converter chip, which is also controlled by the SPI bus to obtain a digital signal. The voltage is then fed into Honeywell's specified output to pressure transfer function to acquire the final pressure readout. Once all the external data is acquired from all the sensors, it is fed into our conversion equations to acquire a measured viscosity. All data is saved into a CSV or comma-separated value file, which is then exported by the Python Pandas library into a Microsoft Excel format for additional analysis.
So, what's the takeaway? Well, viscosity measurements provide customers with a means to evaluate their particular wax's resistance to flow. This becomes of greater importance when waxes are mixed, combined, or machines are left to cool and reheat over the course of a production run. Because any combination of these factors may cause a change in the wax's chemical composition, injection parameters which have previously yielded quality results may introduce casting defects. By measuring wax viscosity at fixed intervals during production, any shift in viscosity can be measured and corrected. Here is the testing procedure. By using our user manual, operators can run the series of tests, whose outputs are automatically converted into viscosities. Extensions of this viscometer include the possibility of creating a full temperature versus viscosity plot for a particular wax, allowing a detailed relationship to be formed between a machine's temperature set point and viscosity. Also, we've created a 3-level, 2-factor designed experiment which develops the relationships between viscosity, flow rate, and temperature around a process center. Designed experiments like these can show controllers how, if viscosity is drifted from acceptable standards, injection parameters may be altered to correct it. So before I go, and on behalf of the rest of our group, I just want to extend my thanks to Dr. Heather Lai, our project advisor, and Vice President of MPI, Aaron Phipps, our stakeholder. And if you'd like to reach out to us, feel free to contact us at newpaltzengineeringdesign@gmail.com.